Today I'd like to talk about what happens when we make small changes to the sines and to the cosines of angles. To start off with here, I've got just a segment of a circle here of unit radius. So radius is 1 as given. Okay, and we're going to have an angle, which I draw here. We'll call it angle theta. Okay, so now with the sine being the opposite over the hypotenuse, the y distance, distance in the y direction, we're going to call that sine theta, and the change in the horizontal distance here, or shall I say the horizontal distance, is cosine theta. So to see what happens, I'm going to go ahead and draw a very small change in the angle, and then we're going to expand it and see what happens. Okay, so here I'm going to draw a very, very small change in the angle, and although this is finite, we're going to assume that this change is infinitely small. Now, the important thing to consider is that when you make a small change, or shall we say, if you take a small segment of a curve, or a small enough segment, that curve is going to look very straight. Okay, it's very similar to the reason why if you take a spherical object such as a planet Earth, someone standing on it will see it as being flat because they're seeing such a small segment of it. So in this case, I'm going to draw this as being a straight line, essentially, even though we know it's not, but it's so close at this scale. Okay, so now, if there's a small change in angle, well, first I'll draw the original angle, okay, and that's going to be essentially perpendicular to this line here. And if there's a small change in angle, well, if that's infinitely small, that will also appear to be perpendicular. It will be like standing on the street in a city and looking at the vertical lines formed by the high-rise buildings. Well, they look parallel, but in reality they converge at the center of the Earth, just like how these converge at the origin. Okay, so now, if I were to make a small change and measure what the horizontal distance is, it would be like going from here to drawing a line corresponding here, very much like this line and that line. Similarly, if I were to do the same for the vertical, okay, I have one line here and one line here, very much like drawing one line here and another line going here. Okay, so now what we would have formed is a triangle, and in reality, if this was drawn accurately, this triangle would be identical in shape to that one, okay, except it's smaller and it looks like it's rotated 90 degrees to the right, or shall I say 90 degrees clockwise. Okay, so that would be theta. So now, if there's a change in cosine theta, okay, and mind you, d cosine theta is right here, okay, it's like going from here to here. Well, the horizontal distance is going opposite, so we know it's going to be negative, okay, with respect to the change in theta. Okay, so this divided by that is essentially sine theta, okay, except it's negative. So d cosine theta respect to d theta equals minus sine theta, okay, because it's this divided by that, except I'm going from right to left, which is opposite the positive direction of the x-axis. Now, if I'm going to find the change in the sine theta, it's going from here to up here, okay. So again, now, in this case, the change in sine theta is going to be the adjacent over the hypotenuse, okay, which will be cosine, and in this case it's going in the same direction as the y-axis, so we know it's going to be positive. So d sine theta over d theta is equal to cosine theta. So what we've just proved is that the change in cosine theta with respect to theta, or in this case a derivative of cosine theta with respect to theta, is minus sine theta, and the derivative of sine theta with respect to theta is cosine theta. Well, I hope you find this informative, and I'd like to thank you very much for watching.